Okay, welcome to the next talk in the session. It's by Stephen Murdoch. He's a researcher at the University of Cambridge and also in the OpenNet initiative. And today he's going to present something about detecting temperature through clock skew. And he's doing something which normally medical doctors are doing, like measuring temperature. Okay, welcome.
Okay, hello everyone. So, this is a summary of my talk. Once it comes on the slide. Yep. So, I'm going to talk about clock skew and how it's going to find security vulnerabilities in some systems. So, firstly, I'm going to give some background on what clock skew is and also how it's affected by temperature. And because I'm interested in looking at it over the internet, I'm going to show how to measure clock skew remotely. I'm going to illustrate how this affects Tor, so I'll give some background on how Tor, and in particular how Tor hidden services work. And then I'm going to detail the attack. And finally, I'm going to conclude with a few other ways that it might be possible to use clock skew to do interesting things. So, firstly, for the purposes of this talk, I'm not talking about only real-time clocks that represent the time that you'd find on a watch. A clock is anything which measures a period of time. So the first part of this is an oscillator, and that's controlled by a clock crystal. And this ticks at a certain predetermined rate. And this feeds into a counter, which counts the number of ticks and makes that available to something else. Sometimes this is a special purpose device, but in the examples I'm looking at, this is all controlled by the CPU of a computer. A computer will generally have multiple clocks, and I'm going to talk about a few of them here. I'm going to give examples from Linux, but other operating systems are quite similar. The one important clock is the Jiffy counter, and on Linux this is only available to the kernel. Importantly, it's not corrected for any clock skew, and NTP doesn't apply for this. There's also the system clock, which is the one that is actually available to the user mode programs through the get time of day system call. It's also corrected for NTP, which makes measuring the clock skew of the underlying clock crystal a bit harder, but still possible. But this shouldn't be confused with the BIOS clock, which it runs even when the computer is off, and it sets the system clock once the computer is booted. On older computers, this was a dedicated chip, often made by Dallas, you might see it. On more modern computers, this is integrated with the chipset, like this picture here. So I mentioned that I need to measure clock skew remotely. This means I need to somehow get timestamps from a computer. And there's a few ways to do it. One of the most obvious ways is the ICMP timestamp request. This is a packet where you send it to a computer, and it will respond with its notion of the system clock. One advantage is it's comparatively fast. It runs at 1 kilohertz, and it's from the system clock, so NTP synchronized, which is a bit of a problem for what I'm doing, as you'll see later. Another disadvantage is that on the open internet, ICMP is commonly blocked unless it's known to be a useful thing. And in this case, ICMP timestamps is not essential. So if it's on at all on a host, it might be blocked at the firewall. Another one, which actually brought me onto this topic, I talked about at the last Congress, which is on Linux. You can estimate a notion of a computer's time by the TCP sequence number. This is because when a sequence number is generated, the host will take the source, destination, port and IP address, hash them all together, and then add on a 1 megahertz clock. So that's good because it's very fast and it allows you to estimate the time very accurately. But it's from the system clock, so it's NTP synchronized, which is a problem. But one thing on the good side is it's actually very hard to block on firewalls, because if you block initial sequence numbers, then nothing works. And if you want to know more about this, there's some more information in my previous talk. The slides are on my website. But for the rest of this talk, I'm mainly going to talk about the TCP timestamp feature. This is a fairly new feature, but it's enabled on all modern operating systems that you find now. The specification doesn't say which speed the clock should be. In practice, it varies between 2 Hz and 1 kHz. On Linux, it goes between, I think, 100 kHz and 100 Hz and 1 kHz. It's generated from the Jiffy counter, and this is good because it's not NTP synchronized. And it's also quite hard to block on the firewall because it's a TCP option, and firewalls will typically not manipulate packets. On very fast networks, it's actually essential to have the TCP timestamp, otherwise the sequence number will wrap around and you can get losses of data. It also increases performance. So, some more terminology. Offset is the difference between 2 clocks. So if my watch says it's 12:51 and your watch says it's 12:52, then we've got a difference of 1 minute, and that's the offset. For the rest of the talk, I'm going to measure this in milliseconds. But if my watch has an offset of 1 minute today and 2 minutes tomorrow, then there's clock skew. There's 1 minute per day. This is when the speed of the clock is wrong rather than just the phase of it. This is commonly measured in parts per million, and for, as an example, 1 part per million corresponds to 1 minute every 2 years. So this graph shows 6 computers and their offset over time. Each of these dots is one TCP timestamp request, and trying to estimate the offset from that. There's noise, as you can see, but if you try to fit a line over the top, it pretty much matches the points underneath. And the slope of this line is the clock skew. So there was a previous paper in 2005 by Yoshi Kono, which showed that clock skew of a host acts as a reasonable fingerprint. That's because it doesn't change very much over time on one computer, just 1 or 2 parts per million, but different computers, even from the exact same model, will have a significantly different clock skew, up to 50 parts per million. And this allows you to get 4 to 6 bits of information on a host. So it's not, by no means, completely unique for all computers, but it can give you a reasonable idea. So this has a number of consequences. Firstly, you can identify machines as they move. If you're using your laptop here and then you want to be untraceable, so you take it somewhere else, even if you've got a different IP address, different location, the clock skew will be largely the same. In network research, it's common to release network traces for measuring properties of TCP and various performance measurements. For privacy reasons, IP addresses and other information that could compromise people's identity is removed. But clock skew remains. So that paper showed how you can use clock skew to de-anonymize such network traces. Virtual machines have a very different clock skew pattern from physical machines. So if you have access to an IP address, you can use clock skew to find out whether it's running on a virtual machine or whether it's a physical one. And similarly, you can find out whether you have multiple virtual machines on the same physical host, because they'll have strange characteristics because it's a virtual machine, but it will be the same across all the virtual machines. So some of you might have heard of HoneyNet, or the HoneyNet project, and HoneyD is one tool for using this. And this has now been modified so that each virtual host will be given a random clock skew. You can also use it for counting number of hosts behind the NAT. If you see all the packets coming from this box with the same IP address, it looks like they're all the same host. But if you look at the clock skew, then you might be able to see that there's a few machines behind this. This can be useful for trying to do network mapping if there are some other restrictions. But although in the extended version of the paper they did mention temperature, they didn't really go any further and didn't do any experiments on that. So that's where my talk is going to start off in the new material. This graph on the right-hand side is from a data sheet for a fairly typical clock crystal for a PC. On the vertical axis, you have the clock skew, and the horizontal axis is the temperature. This is over the full operational range of this particular clock crystal, which is minus 50 Celsius to 100. But within a PC, things like the hard disk are going to fail outside, well within that area. So in practice, a PC, although not the CPU, will spend most of its time in this tiny box here. So let's look a bit more closely there. So in one of my tests, I saw that a temperature changed between these 2 points, about 2 degrees Celsius, and there was a corresponding change in clock skew. And that's more or less consistent with what the data sheets say. And this is quite a small difference in temperature, and it's affected by the outside world. So even in the Cambridge Computer Lab, which is a very well insulated building, you can still see the change in temperature over a day. So in order to find out the clock skew of a host, you need to do some analysis of the raw data, because as you can see, it's actually quite messy. So this is probably the important section of my talk. If you understand this slide, then you understand the rest of it. I'm going to describe how to go from the raw network data into a clock skew measurement. So firstly, I measure the offset. These are all these grey dots, and try to fit a line over the top of them. And you can see that I've got these for each of these hosts. Now, the points match this line quite closely, which means that the clock skew is constant, which is not what I want to see. I want to see changes in the clock skew. And this is because the absolute clock skew, how it varies between hosts, is very large compared to how the clock skew varies. So if I subtract this diagonal line and shift all the points up, then I get something like this. I'm now going over a much longer time period, so I can see more data. And you can see that there's noise. This is from 2 sources. Firstly, there's network latency between a packet being sent out and when I receive it. There's a certain amount of time, and this varies. Also, there is quantization noise. I mentioned about different clock speeds. This means when I sample a clock, I might be sampling just before a tick, or just after a tick, or a long time after a tick. And this introduces noise as well. And that's why it's almost exactly 1 millisecond, which corresponds to a 1 kilohertz clock. So, as before, I try to remove this noise by drawing a line over the top. This time, it should be a curve, but it's much simpler to take a number of segments and overlap them. So there's one, and there's another one. And in order to actually find out what the skew is, it's the slope of this line. So if I differentiate it, I get this kind of graph. So as you can see, it's a little bit noisy, but there's something clearly going on around about 8 o'clock in the morning on Saturday. And this is approximately when the air conditioning in the computer lab gets turned on. It certainly isn't, because I'm in the lab at 8 o'clock in the morning on Saturday. If we compare this to temperature, there's actually a reasonable match. So this justifies that maybe this is actually going to work. But how can this be used for more security purposes? Tor is an anonymity network. If you want to browse websites anonymously, then this is a reasonable way to do it. It works by going through a random selection of volunteer nodes. When you want to go to a web server, you first of all look up all the Tor servers. There's around about 800. I think there's one running this Congress right now, I hope. And pick 3 of these at random, and then send your traffic through it. In addition to hiding your path, it also tries to hide your data. So when you send out the data, you wrap it up in layers of encryption. And each time it goes through one hop, one layer of encryption is removed. That means the data going into a Tor node is different from the data coming out. And that tries to hide correlations in the data itself. But Tor doesn't introduce any delay intentionally, although it can be slow at times. And this means it's vulnerable to traffic analysis, which you can hear about in more detail on day 3. This is, you can see a packet coming in, you know what time it came in, and you also know what time it came out. And these should be fairly close to each other, and you can use this to work out what's going on. This slide is one example. This is me browsing the web from Cambridge, but through Tor. And it so happens that my traffic came out in Google, or Google thinks I'm in Denmark. And if I press reload, it will change eventually. Another feature of the Tor network is the support for hidden services. This allows you to run a web server or any kind of TCP server without giving away your IP address. This not only protects the person running the website in case they're hosting some controversial content, but it protects the website itself. Because if you don't know where a host is, then you can't mount a denial of service attack on it. In using a Tor hidden service, there are 3 main steps. Firstly, there's the service publication. This is when the hidden service starts up. From the Tor network, it selects a random host. This is called the introduction point, and it connects to it over the Tor network. And each of these router type things is one of the Tor nodes. It then takes the address of this introduction point and sends it to the directory server. So time passes, but this connection number 1, is left running continuously. When one of the clients, shown at the bottom, wants to connect to the Tor hidden service, it connects to the directory server, again over Tor, and requests the address of the introduction point. It then picks another random Tor node called the rendezvous point. And this can be any node on the Tor network, and makes a connection to this over the Tor network itself. So that means the rendezvous service doesn't know who the client is. And it sends the address of the rendezvous point up to the introduction point that I mentioned earlier. And that then gets passed to the hidden server itself. Then the hidden service connects to this rendezvous point, and now there's a connection going all the way from the client to the hidden service via the rendezvous point, and data can be transferred back and forth. Tor hidden services aren't perfect, and earlier this year there was a paper published which showed one weakness in the Tor hidden service system. This is the 3rd stage from the previous slide up here. You'll notice that there is one Tor node here which has a direct connection to the hidden service. This means that it knows the hidden service IP address. What it doesn't know is the hidden service's pseudonym, because the data going through it is encrypted. If an attacker owns 1 or 2 Tor nodes, then as the hidden service chooses these routers randomly, eventually the attacker will be in that position, and then the hidden service is vulnerable. Because the data is encrypted, it is not trivial to find out when this situation has actually happened, because the data going through it will have no mention of the pseudonym being used. But traffic analysis will work, because, as I mentioned, there's no latency, or no intentional latency introduced. The client, who's also working for the attacker, sends one packet, and then sees how many packets goes through the attacker's Tor node. If it's 0 and it gets to the hidden server, and the actual packet gets to the hidden service, the attacker knows that it's not the one. And it just repeats this until it starts seeing the same pattern at the client that it does at the evil Tor node. And when this matches, the attacker will be able to find out the IP address of the hidden server. So this has now been fixed in the latest version of Tor by a feature called guard nodes, also sometimes called helper nodes. This means that the hidden service will pick a selection of Tor nodes to be its first hop, the star position in the diagram. And it will stick with these for a very long period of time. That means that if one of these Tor nodes is wicked, then it's going to be discovered. But if it's lucky and it's not one of the Tor nodes working for the attacker, then the hidden service should be safe for quite a long time. But it's not always necessary to be part of the Tor network in order to do traffic analysis. This is an attack I worked on with George Nazis, who will be talking tomorrow. And it allows someone to do traffic analysis entirely remotely of the Tor network. There's two steps that the attacker does. The scenario is that a client is, a web server wants to find out who is browsing their web server through Tor. So the way this connection works is like any other Tor connection. The client connects to one of the Tor nodes, and then another Tor node, then another Tor node, and then it finally comes out at the web server. The web server only has the IP address of this Tor node, which isn't much good in order for tracking back where the connection came from. But it can send data through this, and it can send fairly characteristic data. So if it sends through something like looking like this, so that would be sending for a few minutes, stopping, sending for another few minutes, stopping for another random time, then this pattern will propagate all the way through the network and also to the client. Simultaneously, the measurer, also working for the attacker, probes the latency of each of these Tor nodes. There's a fairly large number, but at the moment around about 800. But with a reasonable sized botnet, it wouldn't be hard to do this. If it's probing the wrong Tor node, where the stream is not going through, it will get back a pattern that's not the right one. But if it's probing the right Tor node, like this one, it will manage to see the pattern and know with a reasonable degree of certainty that that Tor node is carrying the stream that it's interested in. This data is from, I think, November 2005, but it's from the real Tor network. On the top, you can see the induced load. This is where the pattern is being sent into the network. So the attacker will send for a few minutes, stop for a random period of time, send for another few minutes. The measurer tries to look at the latency of all the Tor nodes, and this Tor node is on the path that the connection is going through. And as you can see, that there's quite a good correlation between the induced load and the latency. The other thing at the bottom is how the network traffic flows through the network. This is when it's sent, and this is when it's received. So there is some spreading out. This is a very short one, whereas this is longer, but the pattern is largely the same. So if you run this attack for long enough, you can get a reasonable degree of certainty that you've found the right node. One defense against this kind of attack is to do qualitative service features. As you'll know, if the internet is busy, things become slower, and that's exactly what my attack relies on. When a node is busy with processing one stream, it has less time to spend on another one. But this isn't how the phone network works. Your voice calls don't become slower when someone else is using the same exchange as you. And this is because of qualitative service features on the network. it might be possible to introduce this into the Tor network. So when each Tor node will have a fixed number of streams that it thinks it can handle. When each stream is given a fixed amount of bandwidth, the data flows through it, and no matter what happens to any other streams, the maximum data rate will be fixed. The downside of this is it's actually quite inefficient because many TCP connections are bursty. If you think about downloading a web page, you'll download a few images from a web page and keep the connection very busy, and then stop while you try to read that web page. While this is happening, because Tor is doing a lot of encryption, the CPU will cool down. This is due to the temperature, the power management on the CPUs. This will affect the temperature of the whole case by a fairly small amount, and also affect the clock skew of the crystal. This can be used in order to build an attack. This is a slightly different scenario. Now the attacker wants to find out the address of a hidden server. Again, it can introduce traffic patterns. The pattern comes in here, goes through the rendezvous point, through a few Tor nodes, and then comes out here. Now I'm not increasing load on the network, I'm increasing load on the hidden server. And this can be quite substantial because each of these involves one AES encryption for each cell. Okay. And this is some data that I collected from a private Tor network and running that attack I mentioned. I used a private Tor network because currently the performance of Tor isn't, well, in particular the performance of Tor hidden services is quite poor. And this makes it hard to introduce significant load on the host using normal ways. But even if I can't do it in that way, there might be some other ones. For example, when making a SSL connection, before the client has done any work, the server has to do RSA operation, and that's very expensive. So a client can make lots of connections to a hidden service if it's running SSL, and cause it to do these public key operations. This has been used for denial of services in the past, and it still should work. And this means that even for a very low amount of data being transferred, the temperature increase on a host can be quite substantial. But for this example, it's on a private network. On the top, you can see when the load is being induced. Because this attack works a lot slower than the previous one, I have to do the load for a lot longer. Here, each of these is 2 hours. So I send data for 2 hours and then stop for another 2 hours. These grey dots are the offset between the two clocks. You can see there's two factors in here. Firstly, as the clock skew, as the load is being induced, the slope of this curve increases, which is what we expect. The other feature we can see is when the load is being induced, there's lots of grey dots underneath. This is because the host is becoming busy, not only the CPU, but also the network, so it increases latency. The CPU load also has an effect, because by latency I'm including the time between when the timestamp is generated and when the packet is sent out. And it could be there's going to be a few context switches in between these points. As before, I differentiate the green line to form this blue line, the blue triangles. And it matches the load reasonably well. When the load is on, it's high, and then it gradually slopes off as the whole PC case cools down. And you can see up high here again. And I also put a temperature sensor in the machine, and those are the orange circles, and it matches reasonably well. So that's just one example of how clock skew can be useful for security reasons, but there are others. One is inter-process communication. If one process in the computer is warming up the CPU, another process in the computer can measure the temperature of the CPU. This seems basically pointless because there's many other ways of doing inter-process communication. There's sockets, IPC, also simply writing the files. But there are systems where there are communication restrictions on one host, generally within the military situation. These are called multi-level secure systems, and they have quite an adventurous goal. They want to ensure that no confidential information will be leaked, even when the machine has been compromised. Let's suppose that a general who doesn't know very much about computers runs a Trojan horse while he's looking at some highly secret satellite photographs. Even in that situation, these systems are designed to stop this information being leaked out. These work by giving all information a classification level, things like top secret, secret, and so on. And data cannot flow down. So if some data is top secret, it can't go to a process which is only rated for secret information. And only unclassified processes are allowed to communicate with the outside world. So even when there's a Trojan horse running at the unclassified level and a Trojan horse running at top secret level, it shouldn't be possible that data can flow from top secret down to the unclassified one. The normal ways of doing inter-process control on operating systems like this block unauthorized flows of information. So if a top secret program creates a file, an unclassified program won't be able to read it. The same with any kind of normal inter-process communication. But there is a field of research called covert channels, which tries to bypass these protections by using more unconventional means of communication. One that's been discussed a while ago was to use CPU load. So again, I'm assuming that there's a Trojan horse both at a high level and a low level. The process at the high level can use up the CPU time just by sitting in a spin loop. The process at the lower level can try to estimate the CPU load by trying to do some work of its own. If it's getting lots of CPU time, it means that the CPU is free. If it's getting no CPU time, it means the CPU is busy. The high process can then basically signal in Morse code. To send a 1, it uses lots of CPU time. To send a 0, it uses no CPU time. This was a bit of a concern for some of these systems. So they had a defense called fixed scheduling. This is where each process or each security level gets a fixed amount of CPU resources. This is similar to the technique used in real-time systems. Even if a process is not going to do any work, it's still given its CPU time slot, and that means that the process at the lower level can't receive the data. But when it's not using the CPU time slot, the clock skew will change because the temperature will have changed. I don't have any of these military systems or access to them, so I instead simulated 2 completely separate computers by putting this desk lamp in one of my computers. I turned it on for 2 hours, turned it off for 2 hours, and at the same time, from the host, I made a connection to a remote computer that gave me timestamps. Now we see that the temperature changes from the desk lamp, and also the clock skew changes, as we might expect. There is a difference because now the clock skew is the inverse relationship to temperature, and this is because I'm changing the temperature of the machine doing the measuring rather than the machine being measured. For this attack to work, the attacker has to have fairly free access to the network in order to connect to this remote timestamping machine. And in high integrity systems, this is fairly unusual. But this attack can still work because a host will have multiple clock crystals. Not only is there the one that drives the system clock, but there's also one for the Ethernet controller and one for the sound card, sometimes a separate one for the USB. The sound card's the most useful one, because a host can read samples from the sound card and then time how long it takes to get a few samples. This will change as the relationship between the two clock crystal changes and allow it to estimate the clock skew. So not only can this affect one computer, but heat travels. So if you have multiple computers, say a few computers in a rack, then one computer can use clock skew to measure the temperature of the other one. And I haven't done this, but I got an email from someone who said that within rack mount servers, it's possible to induce a 3-degree temperature difference on one machine by changing the CPU load on the one below it. For blade servers, where they share their space much more tightly, it might work even better. So 3 degrees isn't very much, but all this graph is 3 degrees as well. And there is some noise in the clock skew measurements, but it's probably less than a degree. Another idea I had just as I came to the Congress is on the Sputnik. These are clock crystals too. Maybe it's possible to measure the radio frequency skew and work out whether someone is indoors or outdoors. I don't know if the access points for that can go to that sort of level of detail, but it would be interesting if anyone was able to do that. Okay. So I mentioned an attack on the Tor hidden services, which relies on having some Tor nodes controlled by an attacker. There's a number of these, and they work better and faster when the attacker controls more hosts on the Tor network. There is a very extreme version of that called the Sybil attack, where one person creates a very large number of personas and joins a peer-to-peer network and starts taking over quite a large proportion of the connections going through it. And because Tor is vulnerable to traffic analysis, if the attacker controls the first node and the last node on a connection, then it can find out who is browsing what, which is directly contrary to the goals of Tor. I mentioned that there was a paper that showed that clock skew can act as a fingerprint of the physical host. Also, if we can measure the temperature, then we can guess about the environment. So after I wrote the original version of my paper, there was a small panic on the Tor mailing list because round about 30 Tor nodes appeared over a very small number of days. And this looked suspiciously like a Sybil attack. They were all on the same 2/16s, all in the same ISP. The contact information was bogus. The reverse DNS lookups were all registered on the same day and didn't indicate anything about who they were being run by. And also, when a few people, I think Jacob Applebaum for one, traced back where they came from, it turned out they were very close to Washington, DC, which is home of a fairly large number of 3-letter agencies. So the people on the Tor mailing list with the tinfoil hats got quite upset, and one of my colleagues suggested that maybe clock skew would be able to give a bit more information about what's going on. So I ran the scripts against all these nodes and looked at what I got back. These are 6 of the graphs, and there are 2 things you can tell from this. Firstly, it's each host on each host on a /16 had the same absolute clock skew. That suggests that, or it suggests very strongly that they're all running on the same machine. I was able to confirm this by trying to SSH to one of these Tor servers and seeing what host key I got back, and it was the same for every Tor server. They also made a bit of a mistake, which I hope none of you have made, in that they wanted to prevent people SSHing into one of their servers, which is a good thing to do. So they blocked port 22, but they didn't block port 22 from their own machine. So if you use Tor to connect to their own machine, you're inside the firewall. So the other possibility was that there were different machines but in the same environment, and in which case you would be able to see that it was the same, different absolute clock skew, but the same relative clock skew. But since they appeared to be two physical machines, that wasn't really possible. But we can see some other interesting things in these graphs. This jump here isn't actually a jump in temperature. You can tell because changes in temperature will show up as a curve in the offset graph, whereas here there's quite a tight step. So this suggested some changes in routing behavior. Now, of course, you could find some of this through random normal network management tools like ping, but ping measures round-trip time, which is different. Round-trip time is the time it takes for your packet to go to the host and for it to come back. Now, very commonly, these two paths will not be the same. They won't have the same latency. That's because of something called hot potato routing. Every ISP wants to get rid of the packet as soon as possible because while it's transferring it, it's costing it money. So if a fairly large ISP has presence both in, say, the US and Europe, when the packet is going from Europe to the US, it will be transferred to the other ISP within Europe. When the packet is coming back from the US ISP will try to get rid of it as soon as possible, and it will pass it to an internet exchange in the US. So the path it takes over the Atlantic will be different. The latency measured here, or not so much the latency, but the variance in latency, the jitter, is only from the second half of the path, when it's going from the remote machine to your own machine. So combined with the round-trip time, you can look at one side of the path. And this doesn't require any synchronized clocks, which is the normal way of achieving that. So it's now getting a bit extreme. And I should say I haven't actually tried this, but if you know the temperature of the machine, you might be able to work out its location. Clock skew only allows you to find out the changes in temperature. It doesn't tell you the absolute temperature. But if you can measure when the start of the day is, when the sun comes up and shines on the computers, and you can also measure the length of the day, because that changes over a long period of time, you can get a very rough idea of the location. Each of these curved vertical lines is the start of the day at each of these locations. And the horizontal lines are the difference in length between 2 days, 6 months apart. And all these numbers are hours. So it takes a long time to get a significant difference. But if you're only trying to work out what side of the equator someone is on, then it might be a reasonable way of doing it. There's going to be problems of things like air conditioning, but in some cases that can be removed, because air conditioning doesn't work on a continuously variable principle. They have thermostats, and when the temperature is too hot, it will turn on, and when the temperature is corrected, it will turn off. If you look at what the pattern this generates, it's a square wave with a varying duty cycle. When it's hot, it's on for a long time, and you'll be able to see the temperature dropping. And when it's off, you'll see the temperature gradually picking up. So along with NTP and problems like air conditioning, it might be still possible to remove these. This attack will work in some cases. It's probably not the best one, but you might still be worried about it and want to defend against this. It's surprisingly hard. You could try to remove timing information. If you block ICMP, then you'll get rid of ICMP timestamps. There's not really any downside from that. Blocking TCP timestamps is more problematic. Not only are they used for protection against wrap sequence numbers, but by estimating the round-trip time, the TCP stacks of modern operating systems will try to increase the number of packets in flight and improve performance. So you'll have some problems with that. If you block initial sequence numbers, then your connections don't work at all. Instead, you would have to rewrite the sequence numbers, which requires a more sophisticated firewall that can do packet replacement and stateful packet replacement, because the firewall needs to remember the difference between the sequence number it received and the sequence number it must send out. But even if you can deal with all these, there are still some very low-level effects that need to be dealt with. When packets, things like retransmits in TCP, are sent out on timer interrupts or a fixed time period after a timer interrupt, that means that the clock skew will affect the rate that these are being sent out very slightly. There's going to be some noise, but there's a mathematical operation called the Fourier transform that tries to work out the frequency from a number of samples. And the paper by Yoshi Kono had some promising results from just looking at this. So if you can't hide your clock skew, maybe you can try to make it more constant. You could run the CPU at full load, for example, running SETI at home while doing any of your other work. Firstly, this is inefficient, and it also might not always work. In some cases, it might make things even worse. That's because a CPU, by definition, can only run at a maximum of 100%. But depending on what it's doing, the temperature change will be different. I was able to see this when I compared using Tor to introduce temperature changes and using a program called CPU burn, which is specifically designed to increase the temperature. With Tor, I was getting about a 2-degree temperature difference. With CPU burn, I was getting a 5-degree temperature difference. This means that if you run CPU burn in the idle time, when Tor is not running, you're actually making things worse, because the difference between Tor running and CPU burning is 3 degrees, but the difference between nothing and Tor is only 2 degrees. So it has to be done carefully. SETI at home is probably not a good example, or a good way to use this, because it does a lot of floating point operations, and floating point is much more heavy for CPU temperature. More sophisticated devices have something called a temperature compensated crystal. This is an oscillator that's built with a clock crystal and a temperature sensor very near to it. And based on the temperature, it estimates what the skew is and corrects for this. These, in the data sheets, claim to have about a 1 part per million accuracy, which is extremely good. That's a minute every 2 years. But I'm able to detect differences smaller than that. So this might not be enough, but it will depend on how well insulated the PC case is. If you want to go even more upmarket from temperature compensated crystals, very high-end equipment will have oven compensated crystals. These are a clock crystal with a heating element very close to them and a temperature sensor. So they will thermostatically control the heating element in order to keep temperature more or less constant. And these can get 1 part per billion accuracy. And I haven't been able to measure anything like that so far, but maybe with some improvement in analysis, it's still possible. I wouldn't like to say that this is a perfect solution. So in summary, I think temperature covert channels are interesting, and in some cases they're a viable attack in more high-integrity systems. In your average system, there's going to be better attacks, but if you've defended against all other avenues, then this might be an adequate way to go. I showed how inducing load on Tor and Ceres will introduce clock skew, and that can be measured remotely. In the example here, which is from one of the Tor suspected Sybil attack servers, there's quite a lot of noise. This is across the transatlantic, around about 14 hops, but it still allows me to get quite a stable temperature difference out of it. And I showed some other cases where temperature covert channels could be useful. A more higher level point is that even if a system is secure at one abstraction level, it's sometimes helpful to step outside of that, either look more deeply at the hardware or look more at the problem statement and see if that's accurate, because it might turn out that a system that is provably secure in one threat model is actually not secure in reality. So if you want to learn some more information about this topic, yep. The next talk from Roger Dingledine, the Tor project leader, will describe how Tor works, and another interesting aspect of it is how it can circumvent censorship. Tomorrow, George Zanezis will be talking about traffic analysis, which I've hinted at a few times in the talk, but he'll be able to give you a lot more details. There's the paper on which this was based has got a lot more details on how the experiments were run, and there's a short summary of that in the blog posting, which is linked to from the FAR plan. If you want to know more about the clock skew measurement itself, I couldn't fit that in my paper, but the paper by Yoshi Kono gives a very good explanation of how that works. And these slides and all the source code I've used for doing these measurements is online as of today. The code isn't pretty, but it does work. So if you're interested in these kind of cool things to do on security, or you've got any ideas yourself, consider submitting something to Usenix Security. Deadline's quite soon, so get working, but it's a good conference if you have some time to go there. Oh, and one final thing. We eventually did track down the person running the Tor the Tor suspected Sybil attacks, and it was actually an accident. There was no malicious intent, but it was still interesting to find out. Maybe if someone tries it for real, we'll be able to have some tools for defending against that. So that's all from my talk, but I'm happy to have any questions.
Hello. Hi. How much traffic do you need to send to do these measurements? Are we talking 10,000s of packets or millions of packets, or?
I was sending, let's see, 1 packet every 1.5 seconds for round about a day. So very large number of packets. That's actually not very important, the number of packets being sent. What's much more important is the duration of the attack. I think I could greatly decrease the number of packets being sent and still get largely the same results. Because the reason you send multiple packets is to remove noise. Things like the latency can be removed, or jitter in latency can be removed by multiple packets. But a bigger source of the difficulty is how long it takes for some clock skew to have a significant difference in the graph. And that's for 2 reasons. Firstly, CPUs, or a PC has quite a high specific heat capacity, so pumping some energy in it will make it change very slowly. And also, clock skew is very small, things like 1 part per million, so you have to wait for a very long time before that's up to a few milliseconds. So I think you'd still have to run the attack for many, many hours, but the number of packets sent doesn't have to be all that large.
So effectively, you can still detect clock skew even though network jitter would be in the multiple millisecond range through the numerical analysis you were talking about? Yes.
In all my tests for reasonable networks, the jitter had a fairly stable minimum, and that's all I require. Yoshi Kono did a lot more experiments, and they tested on the Planet Lab network, which is tens of computers, maybe hundreds of computers across the university, and they were able to get this attack to work for around about 1 part per million on every node apart from one in India.
I have another idea for defending against these attacks. Couldn't you just use a sort of fan control temperature sensors on the main board and just keeps the CPU on the same temperature level using these fan speeds, and like slowing down the fan if the temperature drops and speeding it up if the temperature rises?
The important thing to keep it at a stable temperature isn't the CPU, it's the clock crystal. And this is harder to keep at a stable temperature because it's almost physically connected to the case. I haven't tried to optimize this attack, but one of the computers I tried did have a temperature compensated fan, and it was varying in speed, but it still wasn't enough to affect this. Maybe with better temperature compensation and a temperature sensor closer to the clock crystal, that could work. It's very similar to a temperature compensated clock crystal in that case.
Would it be possible to measure your own clock skew and compensate for that using, for instance, NTP?
NTP is deliberately very slow in how it finds out its clock skew. It has something called time constant, which is over a period of several days. And this is because NTP simultaneously corrects for clock skew and also clock phase. And it will rapidly become unstable if it tries to compensate over a very short period of time. So I haven't shown any graphs here, but when I was looking at an NTP compensated clock, you could still see when temperature changed. It just was noisy, but I think it would be possible to have an algorithm that knows about NTP and is able to detect when it's being corrected. Because in NTP, you see a jump when it alters one of its variables. So NTP probably isn't good enough. Well, also, I should say that not all clocks are compensated against NTP. The one I was doing, the Jiffy counter, isn't compensated against NTP, and that's intentional because the clock doesn't have to be accurate, but it does have to be more or less stable in order to get the right properties from the TCP timestamp.
Excuse me? What if you use the NTP controlled system clock for all the timestamps? It shouldn't be that much of a problem to modify the TCP stack.
That will cause some problems with TCP timestamps, although they might be a bit too subtle, because the timestamps do need to be more or less stable in order to get the right properties, and NTP will occasionally cause jumps. So that's probably why the authors decided to use the Jiffy counter rather than something else. I think in OpenBSD and Windows, there's a very similar result. If you did do it, then you get noise because of NTP, but I think it would be possible to remove that because NTP reacts too slowly compared to the effects that I'm looking at. I expect that there will be some stability problems if you try to correct much faster than what NTP currently does.
What do you use yourself for as a reference when measuring clock skew?
I was just using my own crystal clock. I was taking advantage of the fact that the room that I'm in is quite well insulated. Overnight, it will only change in 1 or 2 degrees, which will cause some errors in my result. If anyone has better clocks, for example, a radio receiver that's hooked directly into the PC can get a very stable clock. And if you can use that for the experiments, then you might be able to get better results.
Would it be possible to use GPS receivers or network time clocks from DVB RCS or similar two-way satellite communication systems as a reference instead of using NTP or local temperature-controlled oscillator, and improve clock accuracy using those kind of network or radio-based clock?
They have avoided a lot of the problems of NTP. The reason NTP can become unstable is because it also has to take into account of network latency. Things like GPS or MSF don't have those problems. You still have the problem of how do you apply this compensation at sufficiently low level that it's not going to have externally measurable devices? So if you can feed it directly into the clock crystal before it goes into the interrupt controller, then that will probably work. If you start doing software control, then that will affect some clocks, but not all of them. And looking at the Fourier transform of the packet emission timer might still be able to identify that.
What would be the cheapest way to harden a hidden server against clock skew measurement? Would it be to control the temperature of the crystal or to get a better timing signal through another clock?
With hidden servers, I was assuming two things from this attack. Firstly, that I've got a reasonable number of candidates for the hidden server, and secondly, that I can get timestamps from them. One nice feature of hidden servers is you don't need to have an external IP address in order to run them. The connection goes out from the hidden service to the rendezvous point, to the rendezvous point and introduction point. So one way, which will give much better properties, but maybe not 100% security, is to run it behind NAT, because then you are run it behind quite a tight firewall. The other thing I assumed is that the attacker has a reasonable number of candidates. If this could be from two sources. One is if, for example, the attacker knows that only, say, it's a Chaos Computer Club member who's running this controversial website, then there's a reasonable number of computers that they can look at over time. Another possibility is a lot of Tor hidden servers are running on Tor nodes themselves, and this gives them a slight amount of plausible deniability, since someone looking at them can't tell whether it's a hidden service or someone doing basic analysis can't tell whether it's a hidden service or routing other people's traffic, in which case there's going to be a list of them. So two things to do is run it behind that and also don't publicize it. But this only defends against this attack. It might make things worse for other types of attacks, so you need to compare the risks in all cases. Okay, I think that's everyone. I'm out of time, so thank you.